Yellowstone just did something it has never done before. The ground didn't crack where every camera and every sensor had been watching for 2 years. It cracked somewhere else. Barren, unwatched, unnamed ground with zero history of ever doing anything. In seconds, it tore open. In days, it caved in on itself. Within a week, it was firing boiling water 30 feet into the air, completely on its own. And this time, it happened 100 meters from the most advanced monitoring equipment ever placed at a site like this, the closest range science has ever had on an event like this while it was actually happening. What these instruments may have just captured could be the first real breakthrough in predicting the next one. Stay till the end, because what happened after the explosion is far more disturbing than the explosion itself. Welcome to Infinity Alert. Today we're exploring one of the most quietly significant events to happen inside Yellowstone National Park in years. Not because of its size, but because of exactly where it happened and what it might teach us about predicting the next one. Just before sunrise on Saturday, June 13th, 2026, at 5:09 a.m., Mountain Time, monitoring equipment inside Yellowstone's Biscuit Basin picked up something unusual. Not the slow, steady background signature of a thermal basin doing what it normally does, but a sharp burst of seismic energy paired with infrasound, a pressure pulse too low for human ears to register. The signal was coming from the direction of Black Diamond Pool, a name Yellowstone watchers already knew well. In July 2024, that same pool produced one of the most dramatic hydrothermal explosions ever caught on camera, hurling water and rock 400 to 600 feet into the sky and destroying the boardwalk where tourists had been standing minutes earlier. The basin has stayed closed to the public ever since, so when the instruments lit up before dawn, the obvious assumption was that Black Diamond Pool had gone off again. But the data didn't fit that story. The temperature sensor inside the pool barely moved. Something had clearly exploded. The seismic and acoustic readings left no doubt about that. But it wasn't the pool everyone had been watching. A monitoring camera, installed only the year before, caught the real answer. At 5:09 and 50 seconds, a dark plume of steam jetted upward from flat, unremarkable ground just north of the pool. Ground with no warning signs. Ground nobody had been paying attention to at all. When geologists reached the site, they didn't find one new opening. They found 3 freshly formed vents punched into ground that had been solid the day before. Hot hydrothermal water surged out of them and flowed downhill into the Firehole River. The largest of the new features was a fissure roughly 18.5 meters long, about the length of a school bus, gaping up to 1.5 meters wide in places. The water pouring out of it measured close to 90 degrees Celsius, essentially boiling point at Yellowstone's elevation. Downstream, the Firehole River turned a pale milky gray for nearly 6 kilometers, drifting steadily toward the Midway Geyser Basin, visible proof that the shallow plumbing system beneath the basin had just flushed a large volume of sediment-choked water out of itself in a matter of minutes. That discoloration is, in a sense, a physical receipt for what happened underground. Direct evidence that whatever network of cracks and channels sits beneath Biscuit Basin had just emptied part of itself into the river, in a location entirely separate from where anyone had been looking. By the size of the blast alone, this was a minor event smaller than 2024, the kind of small hydrothermal explosion that happens somewhere in Yellowstone roughly once a year. The rocks thrown out by the June 13th blast only scattered a few meters from the vents, nowhere close to the debris field from 2024, which covered roughly 1 square kilometer. If you judged this purely by the size of the bang, it would barely register as news. But the ground wasn't finished. In the days that followed, scientists watched something form that hadn't been there before. A new pool, boiling and gray, appearing near the middle group of vents not through an explosion but through collapse. There was no ring of ejected rock around it, no apron of blasted material, the usual signature of an explosion crater. The ground itself had simply caved inward into the hot zone beneath it. That pool, measuring about 6.5 by 5.3 meters, formed sometime between the afternoon of June 14th and the morning of June 16th. A window scientist can only bracket because nobody actually witnessed the moment it happened. By June 18th, it had begun erupting on its own, sending boiling water 6 to 9 meters into the air in repeated bursts roughly the height of a 2- or 3-story building. Lay the sequence out end to end, and the real anomaly becomes obvious. An explosion on day 1, a fracture and 3 new vents. 2 to 3 days later, the ground collapses inward and gives birth to a new pool. 5 days after that, the pool starts spouting entirely on its own. The hazard didn't end when the initial blast stopped. The system kept failing, kept shifting, kept opening new mouths in the earth for the better part of a week. And this wasn't an isolated incident in an otherwise quiet corner of the park. Since the original 2024 explosion, Black Diamond Pool has erupted repeatedly. There was an eruption in May 2025, a muddy eruption in December 2025, most of them going largely unwitnessed, simply because the area has been closed to the public since the first blast. That closure itself tells you something. An entire basin inside America's most visited national park, fenced off from tourists for nearly 2 years, is not a precaution any park service takes lightly. It's the clearest possible acknowledgement that this specific patch of ground has not settled down, and every smaller eruption since has only reinforced that judgment. To understand why any of this happened, you need to understand what's sitting just beneath Yellowstone's thermal ground. Hot water is constantly circulating through a maze of shallow cracks in the rock, carrying dissolved silica picked up at depth. As that water rises and cools, the silica comes out of solution and coats the walls of these underground channels, slowly building a hard, glassy mineral seal over time. Here's the problem with that seal. It's essentially impermeable. As it thickens, it can cap off a channel that had previously been venting heat and pressure safely to the surface. Once that pathway is sealed, the superheated water and steam trapped beneath it have nowhere to go. Pressure builds, temperature climbs. What you end up with is a natural pressure cooker sitting just a few feet underground that people walk across every day, and it looks completely ordinary from the surface, right up until the seal fails. When it does, pressure drops instantly. The superheated water flashes into steam, and that steam expands with enough force to blow the ground outward, or, as happened here, to destabilize it and cause it to collapse inward instead, days after the initial blast. This is also why a collapse is, in some ways, more unsettling than an explosion. An explosion is violent, but over in seconds. Frightening, but brief. A collapse means the ground beneath the surface had already been hollowed out or weakened enough that it could no longer hold its own weight, so it gave way on its own schedule, days later while looking completely solid in between. A person could, in theory, have walked directly across that patch of ground the day before it caved in and felt nothing unusual underfoot. That's the uncomfortable part of this mechanism. The surface gives almost no clue about what's happening a few feet below it, right up until the moment it does. It's also worth being clear about what this event was not, because that distinction gets lost online almost immediately. This was not the supervolcano stirring, and it was not magma on the move. Yellowstone sits above a genuine volcanic hotspot, and its magma system is real. But hydrothermal explosions like this one happen in the shallow plumbing just beneath the surface, driven by groundwater and pressure, not by molten rock pushing upward from depth. The two systems can be connected in a broad sense, but a small steam explosion in a thermal basin is not evidence that the deeper system is becoming more active. Conflating the two is exactly how a routine, well-understood geological process gets reframed as an impending catastrophe. Here's the detail that makes this event scientifically significant. The distance between the explosion and the nearest monitoring station was roughly 100 meters, installed only the previous year. According to the U.S. Geological Survey, no hydrothermal explosion in recorded history has ever happened this close to dedicated scientific instruments. Compare that to July 2024, when the much larger Black Diamond Pool explosion tore through the same basin with no hydrothermal monitoring station anywhere nearby. Scientists were left reconstructing the event from scattered debris afterward, with almost no real-time record of it. Distance changes everything about what an instrument can actually tell you. A seismometer sitting miles away records a faint, blurred wiggle on a chart, enough to confirm something happened, not enough to say precisely how. A seismometer 100 meters away captures the sharp, detailed signature of rock fracturing in close to real time. An infrasound sensor positioned that close can register the exact acoustic pulse of steam breaking through the surface, rather than a muffled echo arriving seconds later. A camera on site doesn't just confirm an event occurred, it timestamps the plume down to the second and shows precisely which patch of ground gave way. This time, a seismometer, an infrasound sensor, a temperature probe, and a camera were all running simultaneously within a football field's distance of the blast. That combination gives researchers something this field has essentially never had, a high-resolution, close-range recording of exactly how a hydrothermal explosion behaves, from the seismic pattern in the moments before, to the acoustic pulse, to the frame-by-frame visual sequence. The central question now is whether that data shows a precursor, some small signal in the minutes or hours beforehand that the seal was about to fail. A slow shift in temperature, a change in the infrasound reading, a flicker of micro-earthquakes. If a signal like that shows up, it could give the Yellowstone Volcano Observatory its first real foothold on forecasting these events, even minutes ahead of time. If it doesn't, if the ground stayed silent right up to the moment it failed, that confirms a harder truth, that these explosions can occur without any detectable warning in terrain where millions of visitors walk every summer. It's also worth being direct about what this event was not. Yellowstone's volcano alert level has remained at normal throughout. The aviation color code remains green. In May 2026, the entire park recorded only 45 small earthquakes, the largest just magnitude 2.0, nothing you'd even feel standing on top of it. There's no earthquake swarm, no significant ground deformation, and no signal from the broader magmatic system suggesting magma is moving toward the surface. A hydrothermal explosion like this one is a shallow, local steam event driven by groundwater and pressure a few feet down, not by magma. It is not a precursor to a caldera-scale eruption. The supervolcano is not waking up. The data doesn't support that claim, and repeating it does a disservice to what's actually interesting here. To put this in proportion, small hydrothermal explosions on this scale happen somewhere in Yellowstone roughly once a year. Events large enough to leave behind a visible debris apron, similar in scale to the 1989 Porkchop Geyser explosion, come along roughly every several years. Explosions large enough to leave a lasting crater happen on the order of once every few centuries. And the largest hydrothermal explosion crater ever found on Earth, Mary Bay, along the north edge of Yellowstone Lake, about 1.5 miles across, was blasted out roughly 13,800 years ago, a scale of event that occurs perhaps once every several thousand years. Measured purely by size, June 13th sits at the small, frequent end of a very long historical scale. Alongside dozens of similar events the park has quietly absorbed over the decades without incident. What actually makes this one worth this much attention isn't the blast itself. It's the combination of two specific things. This is the closest a hydrothermal explosion has ever occurred to dedicated scientific instruments. And it's the first time scientists have watched on camera and in real time a new pool form purely through collapse and then begin erupting entirely on its own in the days that followed. That's the genuine first here. Not the explosion, but the detailed record of everything that came after it. The real hazard at Yellowstone was never the one in disaster movies. It's not a magma chamber miles underground. It's a thin, sealed crust of superheated ground holding back near boiling water in places where people casually walk every summer, and which can give way with little or no warning. In 2024, that ground destroyed a boardwalk minutes after tourists had been standing on it. This time, no one was there, but for the first time, the instruments were, and Biscuit Basin will likely stay closed until scientists better understand what that data actually shows. What happens next matters more than the explosion itself. If the close-range recordings reveal even a faint precursor signal, a subtle shift in temperature, a flicker of micro-earthquakes before the seal failed, the Yellowstone Volcano Observatory could take a genuine step toward forecasting these events before they happen, in a park that sees millions of visitors walking directly over ground like this every summer. If the data shows nothing at all, that's an answer too, just a harder one, that this kind of failure can strike without warning no matter how well you're watching. Either way, this is the first time researchers have actually had the data to ask the question properly. And that's what's genuinely worth watching. Not the myth of the supervolcano, but the ground itself, still quietly rewriting its own rules just a few feet beneath where people stand. Thank you for watching Infinity Alert. Stay curious. Stay inspired. See you in the next journey through the universe.